we're gonna have a quick run through of this because we're gonna look at there are three things we can do with what we're looking at here is integration. Not really integration, but we're looking for that's where we're getting to eventually because we're going to go to the trying to find the antiderivative, the integral. Because remember, the derivative finds what? It finds a slope rate of change.
Oh, yeah.
Yeah, so that's what the derivative it finds for us. Because here we can find the rate of change, the slope of any point on a curve. We're going to get to eventually the integral. Well, it's also called the antiderivative. Oh yeah, yes, of course. What the integral is the reason I call it the antiderivative is because it goes the opposite direction. What the antiderivative finds, it finds the area under a curve. In an interval. This is what we're going to talk about first, because as I said, the first two sections, if it was up to me, I'd say let's not do those because they're very lengthy and it's kind of like when we talked about the difference quotient and in order to find the limit, the epsilon delta in order to find a derivative. Then we found the shortcuts. It made it much easier. Same thing with antiderivatives, with integrals, is I can just jump straight to the shortcuts, or we have to talk about where it came from. So let's talk about where it came from. Well, we'll get to that eventually. Let's first talk about a rectangle. Because this curve will be much more difficult to find the area of the region. It's much easier when we do this. So the area is simply x times y, the base times the height, right? But now what does this really mean when it says the base times the height? Let's look at the function from x equals 0 to x equals 2. Find me the area. So this line here, 1, 2. So this crosses at 3. And the domain is from 0 to 2. Now, to find the area, what we've learned so far is 2 times 3, so the area is 6. Well, there's another way we could do it, which we're going to do it in parts. This, we could have broken it down to two separate ones. We'll find this area and this area. And if we add up those two sub areas, we'll get the overall area. because the formula for area is the base times the height, which is the base deals with the x value, the height deals with the y value, or the function. So here on the bottom, the delta x from the beginning to the end is 2 units. And the function itself, f of x, is equal to 3 because it's a constant function. So here the area is delta, or the f of x delta x. 3 times 2, which is 6. So in other words, if we cut it up into smaller partitions, we should get the same answer. So delta x is, how wide is delta x? From 0 to 1 is 1 unit wide. So delta x is constant. It's 1 unit wide from 1 to 2. It's always x2 minus x1. That's delta x. So 1 minus 0 is 1. 2 minus 1 is 1. So delta x is equal to 1. And since f of x is a constant function, the horizontal line, so for area 1, we have f of x delta x, 3 times 1 is 3. And area 2, same thing there. It's f of x times delta x. 3 times 1 is 3. So if we add up a1 plus a2, our area is 6, the same thing as that. So that is what our idea is all about. Didn't think I was looking online to see if you were online.
Sorry, I'm late.
Oh, no worries. Oh yeah, I wouldn't doubt it. So. Oh yeah, we're just gonna do the highlights of chapter 5, sections 1 and 2, if we can. Because we only have 6 sections left of the course. It's all of chapter 5.
Right.
And that's just, it's dealing with basically integrals. So antiderivatives.
Estimating the area.
Under the curve, right? And it was not deriving where that comes about. Yeah, what we have here is we have a rectangle. So our function is a constant function. It's a horizontal line, 3. Our domain is from 0 to 2. Because we're trying to find the area inside this box. Since it's straight curves, since it's straight lines everywhere, it's a very safely bounded function. What we do here is our function, and well, as I said earlier, it's base times height. That's the formula for area. The base has to do with the x values, and h is how far it goes up. that has to do with the y values. So since x is 2, y is 3, we know that the area is 6. Using function notation, y is f of x. Again, if we have straight lines, this is what we need. It's all we need. What if we split it up into 2 sections? Because now we have a subdivision of our domain. And that's what we define as delta x. It's x2 minus x1. It's a change of x. So the delta x in the first one is 1 minus 0. And the delta x on the second interval is 2 minus 1, which is also equal to 1. And since this is a horizontal line, our function is the constant function 3. So the area, as we just talked about when you were walking in, is made up of the sum of those 2 areas. The area of the first one is the base, the height is f of x times delta x. We'll call those 1. And then f of x2 delta x. Remember, we calculated our area to be 6. So in this first area, 1 times 3, so this is 3. The function itself is 3. The delta x is 1 unit wide. So same thing with the other one. So 3 times 1 is 3, plus 3 is 6. So we got the same answer. Let's go further. We first cut it up. Let's cut those in half. So now we go to 1/2, 3/2. So this is, we're partitioning our graph into smaller pieces.
Then adding.
Right. So we have area 1, area 2, area 3, area 4. Again, the formula for area is still the same. It's f of x times delta x. Our f of x is a constant function. Since it's a horizontal line, it's 3. So the only thing that really changes is our delta x. The function never changes. So the only thing we can change is the number of partitions that we create. So what is it? What's our delta x going to be in this one? Well, because it's 1/2. So delta x is always x2 minus x1, which is 1/2 minus 0, which is 1/2. Same thing, 1 minus 1/2 is a half. 3/2 minus 1 is 1/2. So our delta x is always going to be 1/2. So we have f of x1 delta x, f of x2 delta x, f of x3 delta x, and f of x4 delta x. Three times a half, 3 times a half, 3 times a half, 3 times a half. So that becomes 3/2, 3/2, 3/2. We have a common denominator, 2. So we just add the numerators. 3 plus 3 is 9, 6 plus 9 plus, so it's 12/2, which is 6. Now, if we cut it into fourths, it's going to be the same thing. An eighth, eighth. So now, why is this important to know?
Because the area under the curve does change. And you can basically calculate it by getting like smaller and smaller.
Right. And the only thing, because f of x is constant, it's a function, it never changes. If it's x or 3 minus x squared, it's always going to be, so this graph is going to look like that. Of course, it goes to both sides. We only want it from that side. So this one will go to square root of 3. Now, if we had something like this, where it's symmetric on both sides, all we have to do is find this area and double it. So if we just found this area, because this area is going to be the same, so twice area is the whole thing. So what we're getting to is this, and you notice how we add up all these equations. So the area under the curve is, I'm going to introduce this symbol. I know it's a little premature, but I'm going to jump in straight into it and define it. This is the Greek letter sigma. But in Latin, it's the letter summa. Which is what we use the summation of. So the sigma notation, you have a index. What is an index? It's a counter. You start from anywhere you want to, and you go to a number, n. What this thing tells you is to let's say I had this. 2 sub I. I forget sub I. Let's just use 2. Let's not deal with subscripts just yet. And I say that n is 5. Because normally what I would do with this one, I would have I equals 0 to 5. What that means is I would add the number 2 5 times. Interesting. But if you think about it, what this thing tells us to do, well, let's start with 1. We start with the first one. A plus A plus A. How many times do we add A in this example? N times. Yeah, but whatever this is you start here and you stop here. Yeah, it's the counter. Here's the first one. I equals 1. I equals 2. I equals N. That's where you stop. So basically, by the rule of addition, this is really A times N. If you have a constant and you add it up that many times, it's A times N. So if I had I equals 1 to 8, summation of 3. All this would tell us is I'm adding 3 8 times, which is 3 times 8, which is 24. So that's the most basic of that. That's how it works. But then our equations can get much larger. X equals 150. Again, my index is X. That in other words, what this says is the first time through, X is 1. Then the next time through, X is 2. Next time, I keep on going all the way through till we get to 50. So that's how the summation symbol works. So in our example, we could have used and if you think about it, that's exactly what it means. Well, draw another one. So this is my index at 1, the first one. This is equal 2. This is equal 3. This is equal 4, my counter. So in the first one, what's my delta X? 1/2. And the f of X is 3. So for this one, it's 1/2 times 3. That's for the first index. Now the next index is this bar. Again, delta X is still 1/2 and f of X still 3. And I keep on going. So what this says is I would take my f of x times delta x and multiply it by 4. Okay, so that's the easy way of doing it. That's if we have just a rectangular function. Things become less enjoyable So let's see if this one would be 5 minus, gotta be a curve. This is square root of 5. Yeah. Make it more logical. Because when x is 0, y is 5. When y is 0, x is plus or minus square root of 5. Yeah, we could use easy. There are 3 ways we can approach this. We can inscribe the rectangles. We can circumscribe the rectangles. Or we can average them. And I'm using average pretty loosely here. What inscribe means is in the intervals will go and stay on the inside of the curve. What's bad about that method? Well, yeah, we don't know this area, and this whole area here is gone. So, yeah, so that's why this is called the lower sum. Another way we could have done it Another way we could have done it we can take where it touches on the lower bound. So let's compare both of those. Is the first one any better than the second one? It is a little bit better. Because big things, this whole area here, we don't know. We just waste out the whole area. We don't know this area. We don't know this area. We don't know that. Here, we overestimated here, overestimated there. Yeah, so it's, anyways, better safe than sorry. But there's a third way that's better. What this one says, okay, I take the average. Do you see what that last one does? We call this the midpoint rule. Because here's my 1, 2, 3, 4. So here again, we have the same. This is 1, 2, 3, 4. 1, 2, 3, 4. So they're all in the same intervals. This one's too much. This one's too little. So how does this one work? Okay, from this first interval, I take the average of that midpoint. And where that touches the graph, I draw a horizontal line. Because I miss this, but I have too much here. Hopefully it'll even out. Like look here. I'm missing this, but I have extra here. So saying eventually, if you make them small enough, those differences will even out. So that's the method that's preferred, but it's the most difficult because it's a lot more work. So your delta X is the same in all of these. Only thing that changes is what? Is the f of x value. So the only thing that changes in this procedure, this process, is the function itself. Because yeah, it's a continuous function. It's not a constant function. It's integrable. Remember, what does integrable mean? Or differentiable, I should say, not integrable. We haven't gotten to integrable yet.
Means that you can find the slope.
Find the derivative, right? If it's differentiable, you can find, that means it's not a constant function. In other words, it's not like we had originally, that rectangle. This would be a constant function. The first derivative is 0. So you're right, it has a slope, which means it's not a constant function.
So is the idea that you're, when you keep putting it into smaller and smaller pieces, the little area that you're,
Will eventually goes to 0. I mean, because the wash out.
but doesn't, but since you're having smaller parts, when you add them all up, you still have the same total like area.
Area, yeah. Yes, because yeah, eventually, even if we zoom in, if our number of intervals is 1 million. Missing one. Even if we zoom in, we're still going to have that same difference. You're always going to have, because remember, it's a curve, and there's no way we can make a rectangle fit inside a curve.
Yeah, you can't square the circle.
Exactly, yeah. So we'll always have that moniker of error factor in it. But that's the reason we go to infinity. If we go to infinity, then these get so infinitely small that eventually those go to 0. Theory.
Yeah. Okay. So you always have that little margin of error.
Yes.
Okay.
And which is yes, you will, but then no, you won't, because I'm going to infinity. So that eventually, so I mean, each rectangle is the size of one line.
Right.
So there's no difference. Basically, eventually what you get to is eventually that your delta x is that wide. And so, yeah, so it gets so infinitely small that there is no difference. It's just a point. It's now a point where the delta x here, the change above and below goes to 0. The difference here goes to 0. Let me see. Yeah, because again, my card didn't work in the printer, so it happens every other day. I got there, so I didn't print out anything. So let me make up an example. Oh, f of x equals sine of x from 0 to 2 pi. This is kind of a trick question. Let's draw the graph first. At 0, what is sine? 0. At pi over 2? At pi? 0. At 3 pi over 2? You can see what the area is going to be of this function. What's it going to be?
Oh, yeah, because you have negative area there.
Yeah, we have two separate, one above, one positive, and one negative in the same size. So when I add them together, they go to 0. So how would you go about to find the true area? In order for this to be 0, what has to be true? Here's area.
Same area, the area in A1 has to be the same.
Area in A1 has to be, yeah, the absolute value of A1 equals the absolute value of A2. So if that's the case, wouldn't we change our bound from 0 to pi to 0 to pi? And then double it. So if we found this area, we multiply by 2, we found both of those areas. So if your area ever goes to 0, it's because part of it's positive, part of it's negative. You guys know what I'm saying? That's why I don't like these first two sections. But we have to go through them. Because here, what we're looking for here is actually this, is the integral from 0 to pi of sine x dx. This finds us the area.
So with the integral sign, the counter is on the bottom, and then it's just like
the bounds. Here's A to B. A to B. Yes, starts at 0 and goes to here. But instead of slicing it up with pieces, what this one does, it looks at the entire thing as a function. Remember our unit circle? Where this one is sine, this one is cosine, this one is negative sine, this one is negative cosine. Remember when we learned derivatives this way? Because that's what we call it the antiderivative. It's the opposite of a derivative. The integral is backwards. So the integral goes this way.
The integral is called the antiderivative.
Mhm. So what's the integral of sine x? So here's sine x.
So it would be negative cosine.
Yeah, so this will be negative cosine x from 0 to pi. Now, once you integrate something, okay. Here's the rule. Yeah, I'm jumping over to section 3 or section 4. So basically, here's the shortcut of a rule for the integral. When you take the antiderivative, this is the derivative. What you're going to tell me is what function has this as a derivative. So that's actually f prime. And that's going to give me the function f. So this is actually the derivative. It's actually f prime. So when I take the integral of it, I find the actual function from my bounds a to b. What this means is I start with the upper bound, and I subtract the lower bound from it. And this finds you the area under that curve. So this is the derivative. So if we take the derivative of negative cosine, it would be sine x, check. So now what we would do is we would take negative cosine at pi minus the negative cosine at 0. What is cosine at pi? So this is negative, negative 1 makes it a positive 1 minus cosine 0 is 1, so it's negative 1. Negative and negative makes it a positive, so the answer is 2.
So the area would be 2.
Well, the area of this first part will be 2. So it'll be 2 times 2 is 4.
And we know that the area of the second part is negative 2. But you can't really have negative area.
Right. So that's what the total overall area would be 4. So in short, what this is telling us to do is find the area under a curve on an interval, closed interval, is simply the sum of all is multiply this times this, that gives you the area, times the number of intervals. And the way this is written is the summation of f of x delta x. And it's written as this. And as you guessed, as you said earlier, because the differences are always going to be there. That's why we do the so as your delta x goes to 0, that means all of these little small differences disappear. We eventually have the correct area. This is called the Riemann sum. This is how you find areas. Okay, I just took you through 3 sections, or 2.5 sections really quick. Because I didn't have the outline of what each subsection was. But again, it's the same as the limit, the epsilon delta proof. When have we ever used it again? We've never really talked about it, but we spent 2 weeks talking about it to headaches. So that's why I'm just going to roll over real quick. However, next time I will go over section 2. Section 2 deals with if I give you if I give you this, put that as a summation.
And you don't need to know the calculus.
No, but there are 4 different ways you can do it.
So you can do it with.
But you have to use a summation. Well, you start at 1 to go to 1, 2, 3, 4. But now you have to have the function there. So, like for example, 2i minus I. So the first one is 2 times 1 minus 1. 2 minus 1 is 1. Check. Plus 2 times 2 minus 2. Does that work?
Yes.
4 minus, nope. So instead of I, how about minus 1? The minus 1 is 3. That works. 2 times 3 minus 1. 6 minus 1 is 5. Check. 2 times 4 is 8. Minus 1 is, yep. So here's one formula. What if we started at 0? I equals 0 to 5. or to 4, because we have to have 5 total. So 1 plus 2i, let's try that. One plus 2 times 0 is 1. 1 plus 2 times 1 is 3. 1 plus 2 times 2 is 5. 1 plus 2 times 3 is 7. 1 plus 2 times 4 is 9. So there's another formula. Exactly. So it all depends on where your index starts. You can have a different formula. Basically, you're saying is no matter where you start, you always find a formula.
And your index is that's like how many pieces.
Right.
You're adding.
I have to have 1, 2, 3, 4, 5. I have to have 5. So from 0 to 4 is 5. From 1 to 5 is 5. But yeah, but being able to convert to these rules, these formulas is important because we'll be using that a lot in next calculus. And again, we'll do that next time. I'll print everything out for you for the first 3 sections, and we'll go over that next time. My goal is to hopefully finish everything by Monday of next week. Well, not really. Are you guys going anywhere for Thanksgiving?
Not out of state.